Thank you for the very nice introduction. I would like to thank first the organizers for inviting me here and giving me the opportunity to talk about my work. So today I'm going to talk about the work that recent article that is available on our archive and that I worked with my supervisor, Johannes Schmidt-Hieber. And so I'm going to talk about least squares estimators and talk about some properties of the least squares estimators and apply those properties to transfer learning settings. So let's get in. Okay, so assume you want to conduct some research on a population of, say, cats and dogs. So what you do is you sample some data of characteristics of cats and dogs, and you fit a model, a predictive model. Say you want to predict some illness or some evolutionary trait of cats and dogs. And then you analyze your fit to, well, conduct your research. Say that later you have the idea to do the same kind of research, but this time on a population of lions and wolves. And so the standard statistician would just sample again characteristics of lions and wolves and do basically the same steps as before. Well, an idea is to use transfer learning, which broadly says that because some vague similarity appear between lions and wolves and cats and dogs, then maybe one can use the information of the first estimator to have a nice fit on lions and wolves. And this is the question, the broad question I would like to discuss today. So in practice, this situation happens for multiple reasons. One of them I just cited. Another one would be to push a step further and to have the idea that maybe if I have now a data set on lions and wolves, I can maybe mix both data sets and obtain a better fit, and in this way increase artificially the sample size. And last but not least, some models can take really long time to train, and one can maybe have the idea to save some time and some resources by reusing a previous model instead of spending days training another one. So in general, what we're dealing with is that we have two distributions. First of all, we have two random variables, so x and y, which I call input and output variables. And we have two distributions, p, joint distributions on x and y, and that I call p and q, and that are, so p would be called the source distribution, is the distribution from which we sample in order to fit an estimator. And q would be the target distribution. So it's the distribution on which we use the estimator afterwards. Yeah, there's many, so the transfer learning is a very broad idea, and there's many ways to tackle it mathematically. We focus on one of them, which is covariate shift. Covariate shift says that between the source and the target distribution, the conditional distribution of y given x would be the same, but the distribution of the covariates, so the marginal distribution of x under both distributions, is different. Okay. Yeah, so because we're talking statistics, I have to introduce a framework. So I'm talking about non-parametric regression model. So very classical model. So we have the output variable y is linked to the variable x through a function f0, and there's an additive noise. So we assume that the function f0 is a Lipschitz 1 minus delta function, where delta is a constant between 0 and 1. So the use of this constant I will explain a bit later.
has a Lipschitz constant that is at most 1 minus delta.
Yes, yes. And the noise is a standard Gaussian variable, very classic. And we assume that the distribution of the covariate is supported on 0, 1, so compact support. And what happens is that we collect we sample some data from this phenomenon, and we obtain x1, y1 until xn, yn that are distributed with regards to the source distribution. And well, now the objective would be to reconstruct the function f0, and there is many ways to do that, but maybe the most used one and the oldest one would be the least squares estimator. So this is, we give ourselves a set of functions here, which is now Lipschitz, the set of functions Lipschitz with a constant bounded by 1. And we pick among this set of functions, the one that minimizes this criterion here, so the least squares estimator. Okay, now that I've introduced the framework, I'm going to need problematic. So we would like, so because of this covariate shift, there is assumption there is a bit of a discrepancy between what's done classically with least squares estimators and what we want to do. So to summarize it, in the classical setup, we assume that some new data arrives, and the new data is distributed in the same way as the training data. Because of covariate shift, we have a new degree of liberty here, of freedom, which is that the new variable comes from another distribution. One thing worth mentioning is that this assumption of covariate shift means that basically the input and the output variables are linked in the same way, no matter the distribution of the covariates. And so in classical results, people analyze the risk with regards to the source distribution, which is, so it's the L2 norm with regards to the source distribution. We want to analyze the L2 norm with regards to any distribution. And so very classical, so in this classical way, we obtain the well-known rates. So in our case, it's n minus 2/3, because we talk about the case where dimension equals 1 and smoothness equals 1 because of the Lipschitz assumption. And there is a question mark on what we want to talk about today. And so you see that the whole question now boils down to how to bound this expectation with regards to an arbitrary distribution. And our idea is that if we are able to prove some local rates, in the sense that we have our absolute value of the difference between the estimator and the underlying function would be bounded by another function which would not be random, then we can square on both sides of the inequality and apply an expectation to that. So to obtain such, to have such a result, we then we want to study this weighted soup norm here, which is then the ratio, the soup of the ratio between the absolute value of the difference between the underlying function and the estimator, and the ratio is made with a function Tn, which we will call local rate.
For me, in your statement of this idea, where you get this inequality, you can't have it unless you know F0. You can't have this inequality as a guarantee. It would be a probabilistic statement, right? High probability.
This one?
Yeah. Whereas your F hat can't be simultaneous that goes to multiple F0s deterministically. So this would be with high probability.
Yes, it will be with high probability.
Okay.
That's, yeah, I'm simplifying here, not to get into too much detail.
So when you're taking these expectations, it might be wise to not really think of them as expectations, but as just integrating over X, because they remain random variables with respect to the data generating process that uses the F hats.
Yes.
It's not an expectation for the n sample points of drawn from xi, but it's
Just-
just integrating the x variable out once.
Yes, it's just integrating out X, the new X. But in essence, it's the loss, not the risk.
Yeah. Okay. Thanks for the remark.
So maybe one can ask, so what do you mean in the second line when you write risk?
I mean, it's
It's still a random variable, no? So you're not taking the expectation other than noise as well.
Yeah, it's incorrect terminology. It's not risk, not in the decision theory sense.
Just the L2 norm. Where
okay. Yeah.
This terminology misunderstanding is common in the broader machine learning community. It's like more people should take a decision theory class.
Okay. So yeah, and so in the next so in the following 20 minutes, I will first introduce our main result, which is a little bit abstract. That then I will talk about how what kind of form it can take if we assume more restricting conditions. Then I will talk quickly about the proof, and I will apply this result we'll see what kind of consequence it can have in a transfer learning setting. So, but before I can talk about the main result, I have to introduce two notions. So first notion is the function that we will use as a local rate. So this function is, we call it the spread function, and it's associated to a distribution, a source distribution Px. And so, it's a pointwise solution to this equation here. So in order to get an idea, one can forget about the first quadratic term and focus on the second one. So this is the probability mass, I mean the probability measure of some ball. In our case, it's just an interval. The ball of radius. So we're looking for what is the radius of the ball centered in X, such that this probability measure is equal to log n over n. So if the distribution doesn't allocate too much weight around X, then one has to take a relatively large radius in order for the ball to weight log n over n. And if there's a high allocation of mass around X, then Tn has to be relatively small. I think it's not true in general, but I think a good idea, a good first understanding of how this function works would be to consider the simple case where where the density associated with the distribution is bounded away from 0 and infinity. Then our local rate has this nice form where so it's basically, one can think about it as the inverse of the density. So another thing that I have to introduce, but which is maybe less important for the talk, is that we have to impose some regularity conditions on the probability measures we consider, and we impose the relatively weak condition of, we consider the doubling measures. So what it means is that if I compare the weight of a ball of some radius to the ball of twice the radius, then the ratio is upper bounded by some constant. Basically, it means that if the measure of a ball doesn't grow too fast with the radius. Okay, so yeah, a few comments. So this is not restrictive too much in one way, which is that distribution doesn't even have to have a Lebesgue density in order to be doubling. And it's a bit restrictive in one other way, which is if a distribution is doubling, then it cannot be equal to 0 on uncountable set. So it cannot be 0 on the whole interval. It can be 0 on discrete points, though. Okay, so now, yes.
If I understand correctly, you want to avoid to say that you have mass everywhere. Otherwise, things are too easy.
Yeah.
So if P of X has mass as density on 0, 1, the problem is simple, and you want to find assumptions which are not measured everywhere for P of X, but something which can still allow you to get bounds.
Yes.
Okay, this is good.
Yeah. And I thank you very much for the remark, because actually what we consider is a bit a weakened version of this assumption, which is so the local doubling measure. So in this setup, now we consider a sequence of classes of distributions, and the assumption is required to be verified on only restricted balls of restricted radius. What it means is that now it gives the flexibility to consider distributions where you have a flat part that tends to 0, and so we can analyze, and so we don't lose this information in constant. Okay, yeah. So now I'm ready to introduce the main result. So the main result says that so basically it says that this weighted soup norm with high probability is upper bounded by some constant k. And so to dissect it a little bit, this is a statement which talks this is a uniform statement over our class of locally doubling distributions, and in the worst case over the function we would like to reconstruct, we have this weighted soup norm, which is upper bounded with high probability. And we prove matching lower bound. So the consequence is twofold. First of all, it turns out that this function, the spread function, is the minimax rate, a minimax rate, and that the least square estimator is minimax optimal with regards to the weighted soup norm. So the minimax rate is this function Tm.
In what sense?
So in the sense that
it's not even clear that Tn as a convergence rate is well defined for now, no? So I mean, it's just a number for fixed x and n.
yes. So
what is the rate? I mean, like, you have to tell me kind of what it is asymptotic to if you speak about the minimax rate.
yeah. So because it's a bit more abstract than usual results with an n to some power or anything like that, because now we consider this is, so our rate is indeed a function, and we say that this function is, so if you look at your estimator, you have your least square estimator, and at every point,
Do you have a theorem that you're going to show or not for the minimax result?
Well, this is the theorem.
There's an upper bound, not a lower bound.
Yes, I don't include the lower bound because I thought. I mean,
in some sense, this Tn px is not really clearly defined. No, I mean, so I mean, what you're saying is if you take the infimum over all estimators and then you take the supremum over all px distributions and over all Lipschitz 1 minus delta functions of the expectation of the soup with this Tn inverse f hat minus f0, then this is bounded from below by a constant.
There is at least one case, one function is 0, in which case it's lower bounded by.
This is also a worst case analysis for the design distribution px, or is it for a is it optimal for a fixed px? Because obviously by just like making these design distributions arbitrarily bad or whatever, I can make this lower bound extremely bad. No, so
it's for any distribution in the local class.
So the lower bound is for fixed px.
No, the lower bound is for any px.
And the lower bound, when you take a supremum, then you make it easier to get a lower bound, no? Because the supremum makes it bigger. So
no, for any px, you can design an experiment that is hard enough to estimate. So
do you
that
mean the minimax rate, is there a supremum over the px distribution in your class, or is this a result that is for fixed px?
the result it's a result you take a px, and then you're able to construct an experiment that is hard enough to estimate in order. So and it's hard enough to estimate so that this weighted soup norm is lower bound with high probability.
That statement, there's no supremum over the distributions px in your class.
No.
Like an infimum, that sounds to me.
Maybe it would be fruitful after your talk to write on the board the mathematical statement.
I was actually just going to suggest that we continue with the
Yes.
talk and then we maybe continue with the
Afterwards,
discussion.
I mean, there's several of us would be curious.
Yeah,
to
let's-
listen more about the statement.
Sure.
All right. Yeah, thank you for the remarks. So yeah, and so the consequence is twofold. This least square estimator is a minimax optimal with regards to the weighted soup norm, and the latter is surprising because if you think about it, least squares estimators are designed to minimize empirical L2 norm, which is so it's an average, and you lose information. You don't have any information about local behaviors. And even if it minimizes this sort of weak norm, it's also minimax optimal with regards to the much stronger weighted soup norm here.
So in some sense, on the one hand, you have a local rate, the TNX,
Yes.
which tells you that if you maybe have a lot of samples, if your PX has a high density at some X, then you would hope for a faster rate there because you have more information.
Yeah.
No? But at the same time, you're taking then the supremum over all X, which actually means that in your bound, you get the worst case of all the local rates. So basically, your theorem shouldn't have a supremum. It should be for fixed X. No, I mean,
No, yeah, I see your point. But
Lower bound, yeah.
this if I take it for 1x, then I don't say I cannot really move, cannot really change my x, and so yeah.
I mean, so if you have a point where you actually get a lot of px, then your theorem says that you're doing as bad as you do as the point at the point x where you have very low density. So I'm not actually being adaptive to the region where I have more information in my regression program.
Yeah, I think what about we talk about this after?
I would also agree that maybe you continue the presentation and we record these remarks for the discussion later.
Yes. Okay, and the second consequence is that, well, if I recall if I remind you of the previous problem, we now have this inequality that we can apply.
The problem here, what about the distribution of the data? Is this now a double expectation or an improbability statement?
So we obtain an estimator here that depends on the distribution of the data.
Yeah.
We apply the expectation with regards to a target distribution.
Do you also take the expectation with respect to the distribution of the data?
It's random.
So it's random, yeah.
But the right side's not random.
No, the right side is not random because the
You
function.
can't have that true for all data.
Well, it is with high probability.
Yes. Okay.
Okay. Yeah, I'm simplifying here. So okay. So yeah, and this result, yeah, it's a bit abstract. So I propose to see what happens when I impose more classical conditions on my distributions. So now assume that we consider a sequence of distributions here, and we assume that they are beta smooth with with smoothness index between 0 and 2, and we assume that the minimum of each individual density is lower bounded by some term that tends to 0. In this case, the previous theorem applies, and we can derive a nicer Tn function, which is the same as in the basically the uniform case. And so what is interesting about that is that if you take another Watson estimator and you do the classical optimization of the bandwidth, but this time you allow yourself to optimize the bandwidth pointwise, and you assume that you have an oracle that gives you this the density here, then this is the rate that you would obtain. But of course, for least square estimators, as we see, we don't need to have an oracle for the density, and therefore this is what we call local adaptivity of the LSE. But this is a local adaptivity with regards to the distribution, not the smoothness. Okay, and now I have 2 slides about the proof. So first of all, I talk about the classical way to derive bounds for Lipschitz for least square estimator in L2 norm, and for that I have to introduce for convenience I have to introduce this slightly modified empirical L2 norm. So it's a norm that is indexed by so it's the usual L2 norm if my interval AB here as in index is 0, 1, and I allow myself to pick this to measure the norm of a function only on a sub-interval of 0, 1 on AB. And so what basically happens is that here I have an n, here I have the probability, the mass of this interval AB. So this acts like the sample size on this interval, and I select only the points in the interval. Okay, so usually what is done is that one compares the sum of squares of the least square estimator with the sum of squares of the underlying function, and in this way derives the so-called basic inequality, which says that in expectation our empirical L2 norm is bounded by a Gaussian complexity, and then one can apply metric entropy bounds and chaining techniques to obtain an upper bound. So in contrast, in our proof, we constructed by contradiction, and so we assume that the local rate does not hold at some misbehaving point x star in 0, 1, and because of that we're able to construct a so-called local perturbation Gn that lies in the same space as the estimator. So what I mean by local perturbation is that it differs from the least square estimator only on the small subinterval of 0, 1. And because it differs only on the small subinterval 0, 1, I now, this is why I introduced this norm, I can derive another version of the basic inequality by this time comparing the least square estimator to the local perturbation and obtain in expectation an upper bound by a Gaussian complexity of way smaller space. This way, well, of course it's a sketch, so after some steps, one can conclude that our local perturbation actually has smaller sum of squares than the least square estimator, which is a contradiction, and therefore the local rate has to hold everywhere with high probability. So now that I've, yes?
Quality which you show here, this is not almost sure, yeah. This is not almost true inequality.
It's with high probability.
But then how can you make a contradiction out of it?
Well, we prove that on an even space of probability tending to infinity, this equation holds.
Probability tends to be.
Sorry, to 1.
Wouldn't that be nice? Oh, I'm gonna do better.
Data science would be done if that was.
It's always like that in these course stuff. So you work on an event and conditionally on this event, you do stuff, and this event hold with respect to the data. So the randomness in F.
So this is absorbed in the notation, say.
Yeah.
Okay.
We continue and finish with the talk.
So, yeah, okay. So now I would like to talk about consequences when we look at actual transfer learning setting.
When you get your Gaussian process, so what do you use? You use some generic chaining. What do you do?
Yes, exactly. We use metric bounds and
Okay, so just local metric, and you do.
yeah, the thing is like, okay, to make it short, you can also have a lower bound here based on, because you constructed the local perturbation in a clever way, and there's some interaction between the lower and the upper bound.
It looks like everything could work in dimension D, no? Everything you have a goal all the time. So
Yeah, well, let's talk about this later. I have a lot to say about that. Okay, yeah, so transfer learning setting now. So now assume everything that I introduced before is still available. So we have a first data set, a first least square estimator, F hat, and now we have a new set of data. So we have M point sampled ID from another distribution Q. And what I would like to do is to construct an estimator that uses both the previously, the first set of data and the second set of data, and analyze its performance. So what we do is that we take now the least square estimator on the new sample. So we have now 2 least square estimators. The idea is to estimate the spread functions by, so roughly by taking the definition of spread functions and applying it to, this time, the empirical distribution. And we construct our estimator by making both estimator vote and based on the empirical spread function. So basically what we look, so for a given point X in the space, we we see which estimator has a smaller local rate on this point, and we pick it to predict.
I think we should let him finish his talk because we're already 5 minutes over time.
So we've been pretty relaxed so far this week.
Sure, but I mean 5 minutes over when we still got 5 minutes to go. It's still
Some last half an hour longer.
okay. I'll let the organizers.
No, I'm just having.
Okay, but I'll finish.
Why keep continuing? No, I mean.
I'm almost done. But
It was 45 minutes, that's why. Sorry.
yeah, the goal. So the quick answer is the goal is to see what kind of things we can analyze with our main result. So we can analyze the performance of this estimate. And based on our previous our main result, we can prove that this time it's not uniform over the doubling distributions, but so we prove another minimax result, and we show that this combined estimator, I mean, so the minimax rate for this problem is the minimum between the 2 spread functions, and the estimator we have is minimax optimal. So it's a very simple estimator that is minimax optimal and that can be used for transfer learning in our setting. That was the goal of this introduction. Okay, so now, and to
Using both the data sets. I thought at the beginning of the talk, you were assuming that you wanted to study the quality of an estimator created on the first data set when applied to a new point on a different distribution.
yes.
Here you're using both data sets.
Yes, but this is so yeah, this is the interesting consequence of our main result, that we have this non-random bound on the absolute value of the difference, and we can use it to analyze more complex stuff. Okay, last I would like to, so transfer learning is a bit more popular now in the non-parametric research, and I would like to compare our results with a very recent paper by Patak and Wainwright. So to do this, because our result is a bit specific, we have to talk about an example, and I take as an example the source distribution would be power law. So the density is x to the power alpha with alpha positive, and the target distribution is a uniform on 0, 1. So what they do is that they consider the Nadarya-Watson estimator, and they have an assumption on some similarity measure that they derive between the source and the target distribution. One little remark is that it's really interesting because the similarity measure they come up with is in some sense similar to what I could obtain if I built a similarity measure with our result, but a bit different. So yeah, and okay, and so for this example, in their results, we obtained the following rate, which is n to the -2 over 2 plus alpha. And with our spread function, it's possible to analyze the rate, and we obtain that for the least square estimator, the rate is faster for any alpha big greater than 1. And yeah, and so no comments because I'm late already. So to summarize what we've talked about, I've talked about least square estimators. We've proved that least square estimators are minimax optimal with regards to this weighted soup norm. We deduced property of local adaptivity of least square estimators in the sense that it adapts locally to the density of my data. What we would like to do in the future would be to generalize this result to greater dimensions and to more general smoothness of functions involved in the problem. For that, we would have to use generalized definition of the spread function. And our conjecture is that the least square estimator still is locally adaptive in the case where twice the smoothness index is greater than the dimension. I'm done. Thank you for your attention.